Hello viewers, welcome to this part of the course. Today we are going to talk about AM and FM receivers. In the last lecture we looked at different type of radio receivers, and we also noted that most of the receivers which are currently being used are of super heterodyne type, and we talked about various trade-offs for the selection of intermediate frequency and the block elements for a super heterodyne receiver. Today what we are going to do is we are going to talk about the modified or the blocks which are specific to AM and FM receivers. This has to be seen in conjunction with the discussion which took place in the previous lecture regarding super heterodyne receivers, and after that we will talk about one of the most important uses of modulation, which is frequency division multiplexing. So, here on this slide we see an AM receiver. So, this is a super heterodyne receiver where we have RF amplifier and local oscillator stage which are gang tuned and mechanically linked, and then we have a mixer. So, these three stages are gang tuned, and then the output of mixer is a signal at IF frequency, which is then amplified using IF amplifier and then passed on to the detector, which is envelope detector that detects the modulating signal information, and then it is being amplified and given to the speaker for desired output. What we can see here is that the signal received by the first stage RF amplifier, which is a wideband class A amplifier and whose resonant frequency response curve can be tuned to the frequency range of AM broadcasts, which is 540 kilohertz to 1650 kilohertz for India, and worldwide it can be somewhere from 500 kilohertz to 1700 kilohertz. The modulating signal is then amplified and fed to the mixer stage, which is a class C circuit capable of producing the sum and difference and original frequencies, which is receiving signals from two sources, the RF amplifier and local oscillator. The unmodulated signal from local oscillator is fed to mixer simultaneously with the modulated signal from RF amplifier, and this will produce two frequencies, namely the lower frequency, which is the difference of RF signal, and LO frequency, and sum of that is filtered out, and the remaining frequency will be the difference frequency. The local oscillator frequency based on what RF frequency we are receiving can be varied from 995 kilohertz to 2105 kilohertz. This is an example of super heterodyne receiver where LO frequency is always selected higher than the incoming RF frequency. So, since we want to have a fixed IF at 455 kilohertz, so we choose LO frequency which is having a offset of 455 kilohertz from the incoming RF frequency. Then the output of mixer circuit is connected to intermediate frequency amplifier, which amplifies narrowband signal of select frequencies, which is 455 kilohertz plus minus 3 kilohertz, which is the band occupied by AM or audio signal, human voice signal. In some receivers, this class A circuit acts as not only amplifier but also as a filter for unwanted frequencies which would interfere with the selected one. This new IF frequency contains the same modulated information as that transmitted from the source, but at a frequency which is much lower, which is 455 kilohertz than the broadcast frequency. This conversion process helps reduce unwanted interference from outside sources, and the signal is directed to extract modulating signal and is amplified for listening. So, we can have one example. If we want to tune the receiver AM receiver to 550 kilohertz, in that case the frequency which we are going to choose for local oscillator is going to be 550 kilohertz plus 455 kilohertz, which is the intermediate frequency for AM receiver, meaning the LO frequency will be set to 1005 kilohertz. The mixer will produce usable output at 455 kilohertz and the difference of LO and RF frequencies, and the mixer output is fed to IF amplifier that can respond only to 455 kilohertz. So, there we can get the higher frequency, which is 550 plus 1005, which is 1555 kilohertz is suppressed by this RF amplifier, IF amplifier, and the converted signal is then rectified and filtered to eliminate the unusable portions and amplified for listening purposes. The most important thing here what we need to talk about is the tuning of AM receiver. A super heterodyne receiver, or for that matter any receiver, has a number of tunable circuits which must all be tuned correctly if any given station is to be received. The various tune circuits are mechanically coupled so that only one tuning control and dial are required. This means that no matter what the received frequency, the RF frequency and the mixer input tune circuit must be tuned to it. The local oscillator must simultaneously be tuned to frequency precisely higher than this by intermediate frequency, which in the case of AM receivers is 455 kilohertz. Any errors that exist in the frequency difference will result in an incorrect frequency being fed to IF amplifier, and this must naturally be avoided. Such errors as exist are called tracking errors, and they result in stations appearing away from their correct positions on the dial. Keeping a constant frequency difference between local oscillator and front end circuits is not possible, and some tracking errors must always occur. What can be accomplished normally is only a difference frequency that is equal to IF at two pre-selected points on the dial, along with some errors at all other points. What it means is that we can not have the correct frequency output of the all tuning circuits for the entire range of AM broadcast. If a coil is placed in series with the local oscillator ganged capacitor, or more commonly a capacitor in series with the oscillator coil, then 3-point tracking results. So, here we see a plot in which we have shown 3-point tracking. So, what we see here is that the tuning circuit can produce output which is having a 0 tracking error at 3 frequencies, namely at 600 kilohertz, at a frequency which is slightly lower than 1000 kilohertz, and then around 1550 kilohertz. And this plot has on x axis the tuning frequency and on y axis the tuning error in kilohertz. But what we can see is that for the correctly tuned circuit, the error is limited, upper bounded by 3 plus minus 3 kilohertz. This is what is acceptable, though ideally we would like to have a proper tuning for the entire frequency range, but that is impossible to achieve. Another important characteristics of AM receiver which we have not talked about during the discussion on super heterodyne receiver is automatic gain control. As we know that the signals could be coming from different AM transmitter stations which are located at different distances. So, it is very natural to have the varying signal strength of the input signal. So, what is the automatic gain control? This allows to minimize the variations due to the different locations of AM transmitters, and so that we can produce the same kind of desired output for all the AM stations. So, AGC is a system by means of which the overall gain of radio receiver is varied automatically with the changing strength of the received signal to keep the output substantially constant. AGC enables tuning of stations of varying signal strengths without appreciable change in the volume of the output signal. Thus, AGC irons out input signal amplitude variations, and the gain control does not have to be readjusted every time the receiver is tuned from one station to another, except when the change in the signal strength is enormous. In addition, AGC helps to smooth out the rapid fading which may occur with the long distance shortwave reception and prevents overloading of the IF stage amplifier which might otherwise have occurred. In this particular schematic, what we see is that there is a transfer function of AGC circuit. So, on x axis we have incoming signal strength, and on y axis we have receiver output voltage. Ideally, we would like to have AGC circuit which will allow all the low strength signal to pass as it is, and when the signal strength goes beyond a threshold value which could have resulted in overloading of IF amplifier, then signal must be clipped to have no value higher than the threshold what is kept for AGC circuit. But in practice we cannot achieve this kind of response. What can be achieved is approximation, and this approximation is good enough to take care of the most of the variations which can be encountered in the AM signal reception. Now we move to FM receiver. FM receiver also is similar to AM receiver. Again, it is a super heterodyne receiver model. So the only difference what we see here with respect to the AM receiver is that generally we need much higher operating frequencies in FM. Also there is a need for limiting and de-emphasis in frequency modulated signals. If viewers can recall, we have talked about pre-emphasis and de-emphasis circuits in connection with the response or the effect of interference on FM signals. We can recall that the effect of interference in FM signal is linearly increasing with frequencies, whereas the effect of interference on phase modulated signals is constant. So, good compromise for interference performance would be if we can have a signal modulated as FM at lower frequencies and modulated as PM at higher frequencies. This can be achieved by using a simple pre-emphasis circuit at the transmitter and de-emphasis circuit at the receiver. So, in a FM receiver we will have additional circuit as compared to the AM receiver, which is de-emphasis circuit. We also need to have limiting circuit because the information in FM signals is contained in the frequency, instantaneous frequency, not in the amplitude. So, we can limit the amplitude variations by using a amplitude limiter, and then we use different type of modulator which are different FM modulators, and we also use different methods of obtaining the automatic gain control. So, we will talk about the RF amplifier first. An RF amplifier is always used in FM receiver. The main purpose is of this RF amplifier is to reduce the noise figure, which could otherwise be a problem because of the large bandwidths needed for FM signal. It is also required to match the input impedance of the receiver to that of the antenna. To meet the second requirement, grounded gate or base or cascade amplifiers are employed. Both types have the property of low input impedance and matching the antenna, while neither requires neutralization. The second important circuit which is different in FM as compared to the amplitude modulated receiver is amplitude limiter. So, what we realize is that in a kind of demodulators which we discussed for FM, like slope detector, balanced slope detector, they were in general called FM to AM kind of conversion demodulators. So, for AM to FM conversion based FM demodulator, the amplitude variations can cause distortions in the output demodulated signal. So, what we must do is that we must limit the amplitude variation in the input signal by using amplitude limiters before the signal is being fed to the FM demodulators. So, limiter is a form of a clipping device and a circuit whose output tends to remain constant despite changes in the input signal. In the graph we can see transfer function of one amplitude limiter, where when input varies from 0.4 volt to 4 volt, the output stays constant at 5 volt. When the input is beyond this range, then there will be variations in the output. So, we can see that it is quite possible for amplitude limiters described to be inadequate to the task of limiting the amplitude variations in the input signal, because any amplitude limiter you design will have a finite dynamic range. So, for that matter we might have to use a second limiter. In the case of FM receivers, this second limiter could be automatic gain control. This is to ensure that signal fed to the limiter is within its limiting range regardless of the input signal strength, and also to prevent overloading of last IF amplifier. Now, we move to the last topic of this course, which is frequency division multiplexing. frequency division multiplexing is one of the main reasons why modulation were invented or used. So, whenever the physical medium which is connecting the transmitter and receiver, or the source and destination, has resources which are higher than the resources required for single signal transmission, we can always use some kind of multiplexing techniques to improve the utilization of the physical medium. In the case of frequency division multiplexing, the available bandwidth of the physical medium is subdivided into several independent frequency channels. The independent messages are translated into different frequency bands using different modulation techniques or different carrier frequencies for the same modulation technique to be transmitted simultaneously over the given physical medium. Here in the schematic we can see that there are n channels which are all being multiplexed using frequency division multiplexing and transmitted simultaneously over the physical medium from source to destination. The two devices which are required for achieving this objective are called multiplexer and demultiplexer. So, in FDM the basic approach is to divide the available bandwidth of a single physical medium into a number of smaller independent frequency channels. Using modulation, independent message signals are translated into different frequency bands. All the modulated signals are combined in linear summing circuits to form a composite signal for transmission, and the carriers used to modulate individual signals are called subcarriers. At the receiving end, signal is applied to a bank of bandpass filters which separate individual frequency channels, and the bandpass filtered outputs are then demodulated and distributed to the different destinations. Here in this particular block schematic, we see one scenario in which there are 3 baseband signals which occupy same frequency band at baseband. They are to be transmitted using the same physical channel. So, we can this example considers a SSB type of modulation. So, we can use 3 different frequencies f1, f2, f3 to modulate these 3 different signals, and the resulting signals will have a spectrum which will be non-overlapping, and these signals can be transmitted over the same physical medium without causing any interference. At the receiver side, we will have a filter bank of 3 bandpass filters which are tuned to respectively f1, f2 and f3 center frequencies, and having a bandwidth which is equivalent to the transmitted signal bandwidth. And this way we can separate out the signals for respective destination from the common received signal at the receiver, and then it can be demodulated and fed to the different destinations. In FDM channels, we would like to ideally have these individual channels as close as possible, but if we do that, then there is a possibility of having inter-channel crosstalks due to the filter characteristics which are used at the receiver side. So, in order to avoid this inter-channel interference or crosstalk, we must separate the independent channels by a band of frequencies which are unused, and these are referred to as guard bands. This guard bands are shown in the schematic here, where you can see that channel 1, 2 and 3 all are separated by a guard band. And here we can see one example of the kind of FDM which is being used in the analog telephone line channels, and where we can see that the voice channel which occupies a spectrum of 0.3 to 3.4 kilohertz can be grouped together, and we use 6 such voice channels and transmit them using FDM on 6 subcarriers: 64 kilohertz, 72 kilohertz, 80 kilohertz, 88 kilohertz, 96 kilohertz and 104 kilohertz. This will make a component code which is occupying around 48 kilohertz of band, from 60 to 108 kilohertz. What we can do is that this we can call as a basic 12 channel group, and such groups are then again amplitude modulated onto the subcarriers which are separated by a distance which is around 48 kilohertz. So, these subcarriers could be 420 kilohertz, 460 kilohertz, 516 kilohertz, 564 kilohertz and 612, and whereby we can actually transmit multiple voice data onto the same physical medium using FDM. So, what are the advantages of using frequency division multiplexing? The first advantage is that it is a very simple transmit and receive structure and require very little signal processing. Also, it does not require any synchronization or central timing. Each subband is almost independent of all other channels. The disadvantages of frequency division multiplexing is that frequency synchronization and stability are difficult, because local oscillator must be very accurate. Intermodulation, if of signal which is frequency division multiplexed is passed through a nonlinear amplifier, then transmitter causes third order intermodulation products which can interfere with the desired signal, and the spectral efficiency is lower because of use of guard bands. So, today we talked about AM receiver, and we also looked at specific circuits which are required for AM receiver as compared to a general super heterodyne receiver. We also did a comparative study of FM and AM receivers and talked about the circuits which are specifically required for FM receivers, and realized that except for the amplitude limiting and dim AC circuit, the kind of block or subsystems which are involved in FM receiver are similar to AM receiver. Then we also talked about frequency division multiplexing, which is a way to improve utilization of shared communication channels, and it is one of the most important use of modulation, because by use of modulation we can transmit more and more signals which are over a same physical medium. This is typically required because most of the information sources in which humans were interested at the baseband, they occupy the same set of frequencies, and if they are transmitted without FDM, they will all be interfering with each other and the received signal will not be intelligible. But by use of FDM, we can multiplex many of these signals, whereby improving the power efficiency as well as bandwidth efficiency of these systems. Hope you would have enjoyed this lecture. Thank you.